be talking about electricity for a while. Electricity is kind of important, isn't it? Something that you use all the time. Everything from your video games to cooking your food to running your car, every part of your life involves electricity, your computers and everything. And one of the reasons that we're able to have electricity is because of the way in which the universe has been designed. God has created electrons, and electrons respond to magnetic fields. They work under chemical processes. And we have two basic kinds of electricity. Let me show you that to you. One kind of electricity is generated electricity. Generated electricity is produced when you use magnets and when you use motion to generate the electricity. Let me show you how we can demonstrate that. I have here a generator. This is a device that it has a crank on the handle here, and so I can crank this thing and move wires through a magnetic field and generate electricity. This is called a galvanometer. The needle is in the middle because the electricity can go both ways. And notice what happens as I crank this handle. Watch that needle and see what happens as I turn the handle. Do you see what's happening to the needle? The needle's going back and forth, isn't it? The electricity is flowing one way and then the other way. Back and forth, back and forth. Now that is AC, alternating current electricity, and it happens anytime we generate electricity. So generated electricity is alternating current electricity. The electrons flow this way, and then they flow that way, back and forth and back and forth. And that happens when electricity is generated. Of course, we're using something where I turn a crank on a handle with this thing to generate electricity. But the electricity that comes to your house, which is also alternating current electricity, is generated by a nuclear power plant, by a gas power plant, by a coal power plant, something that generates and turns a wire, and the electricity goes back and forth. But here's another kind of electricity. This is electricity that instead of being generated electricity is produced by chemistry. Now, it can be a battery or it can be a solar cell where light hits a cell and causes electrons to flow out. Let's take our galvanometer and let's see what happens when I connect the battery to this meter that we used a moment ago. And what I'll do here is that I'll take the galvanometer off of the generator and I'll fasten it to the battery. And you watch the needle and see what happens. Now if I turn the battery around, so you see what I'm doing now is changing the polarity, then the electricity flows the other direction. So there's two kinds of electricity. Battery electricity, direct current it's called, which comes from batteries and solar cells, and alternating current electricity where we generate it mechanically. No matter how the electricity is generated, it still follows the same rules. The way in which electricity runs through the wires in your house, the way it deals with light bulbs and things of that type are the same no matter whether it's alternating current electricity from a generator or whether it's direct current electricity from a battery. Let's see if we can figure out what some of those rules are. Okay, now I want to try and help you understand some of the rules that apply to electricity. First of all, you know what happens when I plug this in. And you may know that what I'm going to plug it into is 110 volts. What's a volt? Well, a volt is a measure of energy. You know, we're all talking about energy and how we're concerned about energy. Different energies will help you do different things. So in the United States, the energy across one of these plugs is 110 volts. Do you know what it is in Europe? Yeah, some of you probably do. Instead of 110, it's 220 volts. So their appliances run on higher energies than ours do. So what would happen if you took an American appliance and you plugged it in to a European plug? Boom! Yeah, it would blow it up. A lot of times people go to Europe and they take their hair dryers with them. And the hair dryers are made to run on 110, and they plug it into a European plug, and it's supposed to run on 110, and you're putting 220 into it. They sell a lot of Americans hair dryers over there because it burns them up. But you'll notice that when I plug this in, something else happened. current flows through here. We measure current in amperes. You may have heard amps. Somebody's talking about electrical stuff. Amperes run through there, so the voltage makes it flow, and the amperes are the electrons. It's actually how many electrons are flowing. So it's like if I had a tube of water, and if I had the tube perfectly level, the water would stay in the tube. But if I went like this, the water would flow out of the tube. The difference in energy is the voltage, and that's what makes it flow. The actual material is the current. So watch what happens here. I plug this in, and as you sort of suspected, all of the bulbs burn. And they burn the way you've seen light bulbs like that burn. Now let me show you something else that's kind of interesting. These bulbs have relatively high resistance, and what that means is that it's kind of hard for the electrons to fight their way through the light bulb. Here's a light bulb that has a lot lower resistance. It doesn't oppose the electrons as much. So I'm going to take one of these light bulbs out of here. I'm going to put this one in place of it. Watch what happens when I plug it in. Now remember, this one has less resistance. This one doesn't oppose the flow of electrons as much as these do. And look what happens. Wow, a lot brighter, isn't it? Why is it brighter? Because most of the electrons are going through that bulb. Well, you think about it. If you had a choice of going through a place that's hard to go or go through a place that's easy to go, where are you going to go? Most people are going to go through the one that has the least amount of opposition. And that's why light bulbs have different brightnesses. So if you have a light bulb that's real dim, it must have a lot of resistance, and it's very difficult for the electrons to flow through. If you have a light bulb that's really bright, then it has a low resistance, and lots of electrons go through. Notice something else here. If I unplug one of these bulbs, any one of these bulbs, the others stay burning. Now keep that in mind, because I'm going to change the way this is hooked up. This is said to be a parallel arrangement because the bulbs are parallel to each other. When the electrons come in here, they have a choice of going through here or going through the light bulb. If they go through here, they got a choice. They can go through here or they can go through the light bulb. If they go through here, they got another choice. They can go through here or through here, through here, through here. This is a parallel arrangement. As the electrons come in on this wire, they have a choice of going through this bulb or this bulb or this bulb or this bulb or this bulb. And so they have to go through one of them, but only through one of them. Now watch what I'm going to do here. I'm going to change this. This board is set up so that I can undo some of these bars. So when I undo that bar, now when the electrons come in, instead of having a choice, they have to go through this bulb. I'm going to undo this one over here. And when I undo this one, I've given it another situation. When it goes through this bulb, it has to go through this bulb. It doesn't have a choice anymore. And I'll do that again over here. I'll disconnect this bar on the other side. So once again, I've taken away the choice. And then I'll take this one off. This is called a series arrangement. In order for the electrons to go through, they have to go through all of the bulbs. What do you think is going to happen? I have 110 volts or 120 volts, and now there are 6 bulbs that are going to be using that 120 volts. And watch what happens when I plug that in. Wow, they're not very bright, are they? See, instead of each bulb having 120 volts, they have to split it up 5 ways. And so each bulb only gets a part of it. This is called a series arrangement. And notice what happens if I unscrew a bulb. They all go out, don't they? They all go out, any one of them. And you can understand why that is, because if I break the connection, as the electrons are running through, if there's a break anywhere in the circuit, they can't make it through the circuit. Some of you may have seen old-fashioned Christmas tree lights, that when one light blew out, the whole strand was out. That was a series arrangement. You say, well, why would you ever do that? Well, maybe you don't want the bulbs to burn at maximum brightness. Maybe you want the bulbs to burn not very bright. And so instead of having each bulb have 120 volts and burn really bright, each bulb has a fifth of 120 volts, and it's not very bright. And there are some situations where you want a low voltage to keep things safe. Or maybe you want to be able to turn it off and on. So if you have a switch, you don't want the switch to be in parallel. You don't want the electricity to have a choice of going through the switch or through whatever you're trying to control, because all of it would run through the switch. What you want to be able to do is when you undo one thing, you want it to undo the circuit. Now let's see if you're really thinking here. Get that old brain working here. What do you think will happen if I take one of these bulbs out and put this one that has very little resistance into the circuit? Okay? What do you think is going to happen? All right, let's take this one out, and we'll put this one in place of it. Remember, this bulb does not have much resistance. Now, do you understand what's going on? You say, well, that bulb's not lit. It doesn't have any electricity going through it. Oh, yeah, it has electricity going through it. If I unscrew it, the circuit's dead. But remember, it doesn't have much resistance. So as the electrons go through there, as they fight their way through, do you think they have to work very hard? See, as the electrons go through here, man, they're working hard. They're getting hot. And that filament gets white hot because the electrons are having to really work hard to get through the light bulb. This one, not so hard. They just coast through there. So they don't generate much heat. There's still electrons there because the light bulb still turns the circuit off or on, but not as many. So it's important to understand that how much opposition the light bulbs have makes a difference. Okay, now I got a really complicated one for you. Let's see what you can do with this one. What I've got now is that I've taken the wire in. The electricity comes in on this wire. And look how I've got it arranged. The electricity has a choice right here. It can either go through this bulb or it can go through this bulb. But once it goes through one of those two bulbs, then it has to go through the other three bulbs. Okay? So you track that down now. Electricity comes in on this wire. It has to either go through here or it has to go through that bar and through here. Once it gets through one of those two bulbs, then it has to go through that bulb and that bulb and that bulb. All right, now what do you think is going to happen when I plug this in? Got it all figured out? Okay, watch. Is that what you expected? Now watch. If I unscrew this bulb, they all go out. If I unscrew this bulb, they all go out. If I unscrew this bulb, they all go out. What's going to happen when I unscrew that bulb? Whoa, that one came on. Now, if I unscrew both this bulb and this bulb, then they all go out. Or, if I unscrew this bulb, then that one comes on. Now, I hope you figured out what happens here. These three are in series. So unscrewing any one of them, this one or this one or this one, will cause the circuit to go dead. But these two bulbs are in parallel with each other. So what happens is that when the electrons come through here, it's being divided. Some of the electrons are going through here and some are going through here. And there's not enough electrons going through there to make the bulb glow. Now there's electricity going through because if I unscrew them both, then the whole thing goes out. But if I unscrew one of them, then the electrons all go through the other one. So these four bulbs are splitting the energy four ways. And the same thing, of course, works the other way. If I unscrew this one, then these four bulbs are splitting the energy four ways. But when I put them both in, then the electrons are being divided between these two bulbs. And you probably figured that out. But that's the way electricity works. That's how we use electricity in things like computers and things like houses and things like cars, because we want the electricity to do our work for us. And isn't it interesting that God has designed this thing so that we can use electrons in that way? And we can make our voltages more or less. We can divide our voltages. We can send some current this way and some current that way. This is what an electrician does. This is what somebody who works in electronics does. And the fact that electrons can do that has led us to computers and cars and electric houses and all the wonderful ways in which electricity is used to help make our lives more comfortable. Isn't it wonderful that God has designed electrons and designed materials so they can be used in this way?